So, hello everyone again. This is lecture number 6 from the chapter System of Particles and Rotational Motion. In the previous discussion, we have completed with the understanding of the concept torque and angular momentum. Let's do few problems related to that concept, and then let's understand the next concept, that is equilibrium of the rigid bodies. Okay. So this is lecture number 6 from the chapter System of Particles and Rotational Motion. I am Samir Lawankar. Let's begin our discussion. Okay. So just before starting that, let us do a quick revision of all the concepts we have already completed with. So in the starting of this lecture series, we have started first of all with introduction. So basically, after in introduction, we understood that what is basically translation motion, then rotational motion, then translation motion plus rotational motion. Then in the next concept, we understood what center of mass. In center of mass, if I write a vector notation of this understanding, I can simply write it as nothing but equal to R, which is equal to 1 upon M integration RD. Okay. Then in the concept of motion of center of mass, we finally got that what did we get? F external is basically equal to dp by dt. So in the fourth concept, we got about F external, which is equal to dp by dt. And then in the next concept, we got that if force external is equal to 0, then dp by dt is 0, which can be said as P is constant, and hence the linear momentum of the system is conserved. Then after this, we understood about the vector product of two vectors, in which we understood that A cross B vector is equal to C. Then that means the magnitude of C is basically equal to AB sine theta. And how to find a direction using the right hand thumb. Okay. Then we understood about angular velocity, which is omega. And also we understood about alpha, that is angular acceleration. And then finally, currently we are on the 7th subtopic, that is understanding about torque and angular momentum of the system. Okay, so in torque and angular momentum, first of all we understood about torque, that is nothing but equal to R cross F. And then we understood about angular momentum, that is basically R cross P. Okay, we also understood about the concept of conservation of angular momentum, which can be said as analogous to F external is equal to dp by dt, in which we basically understood that the differentiation of dl by dt is equal to tau external, and if this tau external value is equal to 0, then dl by dt would be equal to 0, and hence we can say that L is constant, or we can say that the angular momentum is conserved. Okay. Fine. So that was a complete understanding, a small quick revision regarding all these concepts. Let's move forward with some questions, and then we can move on to new concept, that is equilibrium of a rigid body. Okay. Fine. So just before going again with that topic, let us first do a simple revision of an analogy between the linear motion and the rotational motion, all the things which we know till now. Okay. So linear, or let's not write linear, let's write translation. So translation motion, and second is rotational motion. Okay, fine. So first of all, we understood here velocity as omega. Here we understood acceleration as alpha. Here we understood next concept was regarding your force, which is torque, tau. The next thing is linear momentum P is equal to angular momentum L. Next thing is force is nothing but equal to dp by dt. Similarly here, torque is equal to dl by dt. Okay, so till now we have understood this complete analogy between the translation motion and the rotational motion. Fine, so let's move forward, and so these all things are understood in the previous lecture only. Now let us go and understand about your first question of practice, that is finding out the torque. Okay, So here find the torque of the force. So what is the force given? The force is nothing but equal to 7 I cap plus 3 j cap minus 5 k cap, right? About the origin, the force acts on a particle whose position vector is given. So basically, R is given to you as I cap minus j cap plus k. Fine. So now let us try to find out the torque. So how to find out the torque value? We know torque is nothing but equal to R cross F, right? So to calculate this value, we know how we will do this. We will draw a determinant. So it's I cap, j cap, k cap. Okay, that's right. So first of all, please be clear. The first is R vector. So you will write R vector first. So it will be 1 minus 1 plus 1. It will be 7, 3 minus 5. So it's I cap into 5 minus 3, which will give you 5 minus 3, plus j cap into 7 plus 5, 7 plus 5, plus k cap into 3 plus 7. Okay, so therefore the final answer you obtain is nothing but equal to 2 I cap plus 12 j cap plus 10 k cap. Okay, so this is the torque obtained for the force 7 I cap plus 3 j cap minus 5 k cap for the position vector of R, which is I cap minus j cap plus k cap. Okay, so you can see clearly that this is a vector being obtained finally. Okay, so that thing being said, now let us move on to the second question. That is, so this is a simple question which involves, this is basically a fact we need to basically derive. So let's look at this and understand what it is asking. So the question is that show that the angular momentum about any point on any point of a single particle. So if we need to calculate the angular momentum of this particle about any point, which of this particle which is moving with velocity v, it remains constant throughout the motion. So they are basically saying that even if you try to change this value of O, right? So if you change this value of O, let's say I calculate from this position or this position or this position or this position, from any position O, the value of the angular momentum remains constant. So the question is basically show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. Okay, fine. So let us calculate this. So here we are assuming that the particle is being kept here, correct? And it is moving with some velocity v in the rightwards direction. Okay, so now we want to calculate the angular momentum of the particle about a point O. So this point O is not the origin here, so we can write it also as something, let's say A dash. Okay, it is just a particle point. Sorry, it's just a reference point from which we are trying to calculate the angular momentum. Okay, so what we can write basically, we can write this angular momentum R is nothing but equal to R cross P. In the place of P, we can write as equal to M into V. Okay, so what is the magnitude? Magnitude is nothing but equal to MVR sine theta. Okay, look at this very, very carefully. That theta is the angle between R and V. Okay, so now although let us say at some part it would have been here, 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 the value of this R sine theta will always be same. R sine theta will always be this only. Let's say I calculate this position or this value from any of the location. This value of R sine theta is always constant when it is moving in the same. Okay. So therefore from this what we can say as R sine theta is constant, we can say that L is constant. So therefore the direction, so one thing more, let us understand. Please look at this and try to tell me what is the direction of movement of your L. So what is L basically? L is basically R cross P, correct? So how we will do it? There are two options. Either it will go inside the page or it will go outside the page, right? Now see very clearly. We know that the vector angular momentum is R cross P. So you will first keep your head palm in this direction and move in this direction. So when you will do this, you will see clearly that you are going into the page. Okay, so the correct answer is your option A. Fine. So this was just for understanding, and so therefore we finally found that the value of magnitude of L always remains the same, and the direction is also inverse. Even by any way, we try to calculate the value of R cross. Thus, we can say that it is conserved. Okay, fine. So that being said, that is the end of this example also. Now let us look at the new subtopic, which is equilibrium of a rigid body. So as we go on towards new subtopics, we are basically trying to implement all the concepts which we have studied in the previous discussions and now trying to implement something new. Okay, so equilibrium of a rigid body. So what maybe you may just think what will happen here, we'll try to find some of the initial equations so that we can say that some body is in equilibrium, right? To be more general or to be more clear here, we are talking this body to be equal to rigid body so that we can simply apply the concepts of rotational motion also, and then also the body will be, or the rigid body will be, right? So let's start this new subtopic, which is equilibrium of a rigid body. Okay, fine then. So let me start. We are now going to concentrate on what? We are now going to concentrate on the motion of the rigid bodies rather than the motion of general system of particles. Okay, so now we'll consider the motion of a complete system of motion of rigid body, either in rotational motion or in translation motion. So we shall recapitulate what effect the external forces have on a rigid body. Henceforth, we shall omit the adjective external, because unless it otherwise, we shall deal with only external force and torques, because in general case, F internal is also 0 in our day-to-day analysis, which we are studying about, and tau external is also 0. If we say generally torque or force, it basically means external force or external torque. Okay. So that's why we may omit sometimes by writing, we won't write external. Okay. So the forces change the translational state of the motion of the rigid body, that is, they change its total linear momentum. It's correct. So the velocity may change or increase, and hence if there is a change in the linear momentum, then we will say that there is a change in the force also. But this is not the only effect the forces have, right? The total torque on the body may not vanish. So sometimes there may be some force which leads to generation of torque, and hence if there is generation of torque, we won't say that the body is in equilibrium. So such a torque changes the rotational state of the motion of the rigid body, that is, it changes the angular momentum of the body. Okay, so now that being said, now let us try to understand about it more. So a rigid body, please look at this line very, very carefully. A rigid body is said to be in mechanical equilibrium if both its linear momentum and the angular momentum are not changing with time. Or what we can say, that the body has neither it has neither linear acceleration nor angular acceleration. Okay, so I hope this line is clear to you. So basically, as we can say that dp by dt is nothing but equal to 0. What does it basically mean? That p is nothing but equal to mass into velocity, which is constant, right? If this is constant, we also know that mass is always constant. We can say that velocity is constant. If the velocity of a particle is constant, then that means what we can say, that the acceleration is 0. Okay. Doing the same concept in terms of your angular momentum, we can say if dl by dt is constant, that means L is constant. What is L? L is basically mvr sine theta. Let us talk in magnitude terms. So if we say that r sine theta is constant and m is constant, we can again say, or let me write it as not this, I will write it as r cross p here. Okay. So here we will observe that alpha is 0. Why alpha is 0? Because the value of omega is constant. Okay, so because r cross mv, and we know that v into r is basically omega. So we can say that omega is constant here, because as v is equal to r omega, and therefore we can write it as equal to mr square omega sine theta, and therefore we can simply write that as m, r and sine theta are constant, omega is constant, and if omega is constant, we can say that alpha value is 0. Okay, right. So therefore when we say rigid body is said to be in equilibrium, it's both linear momentum and angular momentum are not changing with time, or equivalently the body has neither linear acceleration and nor angular acceleration. What does it basically means? It basically means the first point is that the total force on the rigid body, the total force on the rigid body, the total force on the rigid body is zero. Okay, that basically means that F1 plus F2 and so on till Fn is basically equal to summation Fi i's from 1 to n is equal to 0. Okay, so the total force on the body is 0, then we can also say that the total linear momentum of the body does not change with time, right? So hence this above equation gives the condition of the translational equilibrium of the body. So this equation, the above equation, gives the condition for, very important line, so it gives the condition for translational equilibrium of the body. Fine. Also what we can say that the total torque, okay, the total torque on the rigid body is equal to 0. So in mathematical form we can write tau 1 plus tau 2 and so on till tau n, which is also equal to summation tau i's from 1 to n is basically equal to 0. Okay, so the total torque on the rigid body is 0. Then we can say that the total angular momentum of the body does not change with time. And hence this is the condition of, so I will just write here, it is the condition of rotational equilibrium of the body. Rotational equilibrium of the body. Fine. Okay. So I have made you understand this concept also. Now more, let us discuss more about this complete concept. Let us understand more as far as if we try to use this for, so that thing is okay. If we try to separate it into different vectors, if there is difference happening or not, let us try to understand more. Okay. So first of all, there is one discussion we need to carry out. Let us suppose we know that with the change in r, there is a change in the position vector, correct? So will that refer or will that change our rotational equilibrium concept if we try to change the value from which we change the torque? Sorry, we take the angular momentum, or basically we take the torque. Okay, so basically it has been found that the rotational equilibrium condition, so the rotational equilibrium condition is independent of the location of the origin about which the torques are taken. Okay, so the rotational equilibrium condition is independent of the location of the origin about which the torques are taken. Okay, so now we will understand. Let me first make you understand another concept, which is called as couple. So what is basically a couple? Couple are basically two forces which are acting on the rigid body in opposite direction. Okay, so two same magnitude forces acting in opposite direction on a body separated by a distance. Let's ignore the distance as r. Okay, so what is its analogy here? Basically we'll understand the mathematical input in subsequent slides. So I will just try to put in a simple example here. So let us suppose this is that body. Let's say I put a force F here. Let's say I put a force F here, and let us say we say that this value is r. So this is nothing but a couple is being applied to this body. Okay, so we'll understand more about this in subsequent slides. Let's move forward with the concept we are trying to understand here. So here the above equations, which were your force values, so these equations, let us try to use these equations, and these are basically vector equations. Let us not divide these equations into your component forms. Okay, let me write it like this. Let this be equation number 1 and this be equation number 2. Okay, So writing component forms of equation 1 and 2, we get, first of all, for force one, what we'll get summation fi in x direction from I is 1 to n is equal to 0. Similarly, what we'll get, summation fi y I is from 1 to n is equal to 0. And similarly, what we can say, summation fi z is equal to 0 for I is from 1 to n. Okay, where what are fi x, fi y, fi z? They are nothing but the forces, the component of the forces in the x, y, and z direction. Okay, similarly we can write this torque Ix, basically torque of all the I forces, all the particles from I is from 1 to n is equal to 0. Similarly, summation torque Iy is equal to 0, I is from 1 to n. And similarly, summation of all the particles z, where I is from 1 to n is also equal to 0. Okay, where what are these values? They are the component of torques in x, y, and z direction. These are nothing but component of torques in x, y, z direction. Okay. So that thing being said, now basically what we can say that let me write it here. Okay, or let me just add one more page. Just give me 1 minute. So as you can see here, let's say I denote this as equation number 3. This is equation number 4. This is equation number 5. This is equation number 6. This is equation number 7. And this is equation number 8. Right? So before using the first and two equations, we now derive three different equations. Right? Let me just write, therefore, above equations, basically above equation which were summation fi equal to 0 and summation tau I equal to 0, where I is from 1 to n. Here also I is from 1 to n gave us, if I gave only, so gave 6 independent. What does independent mean? It doesn't have any effect on each other. 6 independent conditions, okay, to be satisfied for the mechanical equilibrium, to be satisfied for mechanical equilibrium of a rigid body. To be satisfied for mechanical equilibrium of a rigid body. Okay, so basically now, so in a number of problems, what generally happens, all the forces which are acting on the body are coplanar. And if they are coplanar, basically we can directly use three conditions which are needed for satisfaction of mechanical equilibrium. So now we'll move on to the basic concept which we will be basically applying, or we will in the maximum portion we will be applying in your problems. Okay, so let me just write that and then I can directly explain you that concept. So what generally happens, so in a number of problems, all the forces acting on the body are coplanar. Okay, and hence we need only three conditions to be satisfied. We need only three conditions to be satisfied for mechanical equilibrium. Okay, fine. So understand more about this. So basically these are divided into two types, these two equations. So two equations are basically for translation. So two translational and one rotational. Okay, so let us suppose we are doing this for xy plane. So basically what we will do, we will first of all calculate summation fx equal to 0. Second, we will calculate summation fy equal to 0, and then we will calculate a torque of all the forces acting in the xy. So these are the three equations which are valid in the case of coplanar questions. Okay, so therefore the two conditions are valid. The first is the sum of the component of the forces along any two perpendicular axes in the plane, which is equal to 0, and the third condition corresponds to rotational equilibrium. Fine. So that thing being said, now anything more which I need to make you understand here? Okay, so that is a complete discussion we need to have. Now let us try to apply these concepts in some of the examples. Okay, so just look at this first figure here. So let me make this figure here. So basically what is happening, we need to just calculate. So this is a coplanar diagram only. So we just need to, what is the basic requirement here? What is the basic agenda here? We just need to calculate or see if this body is in equilibrium or not. Right, so let's say this is having some force F, this is having some force F, this position was C, and this distances are given to you as A and A. Right, so now let us try to calculate. Here the mass of the this rod is assumed to be negligible, so it's negligible mass of rod. Okay, so here also C is the midpoint. So basically AC is equal to A and CB is equal to A. Now let us try to calculate what will happen with the translation and the rotational motion. Okay, so here summation Fx is equal to 0. You can clearly see. Let us try to calculate summation Fy. What is summation Fy here? Here summation Fy is nothing but equal to F plus F, which is equal to 2F. If you assume the downward direction is negative, we can write it as minus of F plus F, which is equal to minus 2F. And let us try to calculate summation torque. Let's say calculate it about point C. Then due to this force, it will be in positive direction. That is equal to F multiplied by A in this direction plus F multiplied by A again for this force, which will be in anti-clockwise direction. Okay, so if I calculate the force from here, this will be first of all in this direction, and for this force, this will be in this direction. Okay, so you can see clearly what is happening here. Here the value of torque is 2F into A. Okay, fine. Similarly, let us so basically we can say that this is not even in your translation equilibrium, and not even in your rotational equilibrium. Okay, I think I made a mistake here. This value, so it is clockwise in this sense, so it's clockwise in this sense, and it is anti-clockwise in this sense. Okay, yes. So because those both are different, the rotational motion is 0 here. Okay, so that's why I was waiting. So it's rotational motion is 0 here. As you can see, for this force, what is happening? There's a clockwise movement being applied if we say it from point C. And if we see the same thing for this force, we'll see an anti-clockwise movement being applied. The direction is different. We will have to write plus and minus sign for one of them. And therefore, we can say that the body is only in rotational equilibrium. The body is only in rotational equilibrium. Okay, fine. Moving on more. So let's look at the second point. Let's look at the second problem here. So again, there is a massless rod with the center at C. The first force is acting at this with a length A, and the second force is acting like this again with a length A. Okay, so here let's do again. So what is summation Fx? Summation Fx is 0. Summation Fx is 0. What is summation Fy? Summation Fy is equal to plus F minus F, which is equal to 0. And what is summation torque about point C? So let us first calculate for this force. For this force, it will be in anti-clockwise rotation for F into A. And for second force, it will be in anti-clockwise rotation again. So for this also and for this also, as you can see clearly, if we start from C, then it will be anti-clockwise rotation for the first force, and for second force also it will be again anti-clockwise. So it is 2F into A in anti-clockwise sense. Okay. So using this results, we can clearly see that the body is only in translation equilibrium. Translational equilibrium. Okay, fine. So that was a basic understanding I need to give to you. Now let us understand the concept which we studied just previously, which was basically a couple. Okay. So a pair of, so what is basically a definition? A clear definition is given to you about a couple. So a pair of equal and opposite forces. Please understand this. A pair of equal and opposite forces with different lines of action is known as couple or torque. Okay. A couple produces rotation without translation, right? So if you can clearly see in the previous example, the second example here, you can see that the force was not having any translational equilibrium. It was having translational equilibrium, so it is not having any translation happening, but a rotation is keep on happening. So there is a complete rotation which is keep on happening. So we can say that these two forces acts as a couple. Right. Moving on, so a couple produces, so this thing is explained. Now more understanding is, so okay, so this is one of the example of a simple understanding of a couple. So let us say there is a there is a cap which we need to open. So using our hand, what we basically do, we push the thumb in this direction and we push our index finger in this direction. So basically, if you see clearly, there is a couple being formed here. And what happens with the couple? There is no translation motion of the cap which is happening, only a rotational motion of the cap is being happening. Okay, so that's how we can understand this for your first example. Second example is regarding your compass. Okay, so what generally happens in all the different positions in which a compass can be held apart, except the position in which it is exactly at its north-south pole position. This north pole of the magnet goes or is being attracted towards north pole, and this south pole is attracted towards south pole. I mean, sorry, yes, so means it is basically attracted such that the north direction of the compass shows towards north and south direction of the compass shows towards south, right? So therefore, what is again happening? Again, a couple is being formed here. Okay, as you can see, the forces which are in same in magnitude but in opposite direction are being used, and hence what happens? There is no translation of this compass. There is only rotation happening of this compass. So I hope you can understand this concept also. So basically, there is a rotation motion applied. Okay. So thus there's a couple acting on the needle due to the Earth's magnetic field. So I will just write this. So for this, thus there is a couple acting on the needle, acting on the needle due to the Earth's magnetic field. Okay, thus there's a couple acting on the needle due to the Earth's magnetic field. Okay, so I hope this thing is clear to you. So that thing being said, now let us look at this one more example which you need to understand. So just look at this example. The question is simply stating that we need to show that the moment of a couple, please understand, the moment of a couple does not depend on the point about which you take the moment. Okay. So let us understand that thing also. So we will first understand this and then I will take a simple example. So I will just make that example and explain it again. Okay, so consider the couple which is being shown here. So why is this a couple? Because there are forces equal and opposite in direction being applied. Okay, fine. So here let us assume that we are trying to calculate the moment of this couple from this point O. Okay, so what is the moment from this point to this moment of that we just write. So the moment of couple is nothing but equal to moment of force being taken for this force at B and this force at A. So let us first calculate for this R1. So what it will be? It will be R1 cross minus F plus R2 cross F. Okay, so what we can write it as equal to nothing but we can write it as equal to if I take F common from this, so I cannot take F common like this because then the moment. I can write this as equal to R2 minus R1. Okay, so it's R2 minus R1 cross F. So it's always R2 minus R1 cross F, right? So it only depends on now look at this diagram very clearly. So if we look at this diagram very clearly, what is the direction of R2? R2 is this, right? What is the direction of R1? R1 is this. Okay, then what is the direction of minus R1? Minus R1 is this. Okay, so basically what we need to do, we just need to do R2 minus R1, right? So basically this can be made like this. So it is R2 being kept here, then we need to add minus R1 into this. So this is minus R1. So when we will do this, we will obtain the result of R2 minus R1 is this. So I hope you got how we calculate this result. So basically we had R2, we had R1, we calculated minus R1 like this, and now we need to, what we need to do, we first need to make R2 such that the head of R2 is lying on tail of minus R1, and therefore then this resultant is nothing but equal to R2 minus. So in each and every case scenario, this is basically the resultant which is equal to R2 minus R1. Okay. So that is the explanation here. In other way, we can also write that as R1 plus AB. See clearly, R1 plus AB is equal to R2. Therefore, what we can write? We can write simply AB is equal to R2 minus R1. Therefore, we can write that moment of couple is nothing but equal to AB cross F. So it never depends upon the position from where we take the moment. It is always equal to the value of the distance between them cross F. Okay, so it is independent of the origin. So it is, what is it here? It's moment of couple. It is independent of the origin. Okay. So that thing being understood, just I will again explain you using a simple example so that we can understand this concept. Let us assume this to be a massless body on which there is a force F acting in this direction and another force F acting in this direction. Okay, let us assume this to be the point A. Okay, so this question has nothing to do with the concept we have already studied. It is nothing but a understanding. For more understanding, I made another question. Okay, fine. So let us understand this to be point A at the midpoint at point B at this point at point C. Okay, so let us first calculate the moment about point A. So if we calculate the moment about point A, the moment due to, let's say I write this force as F1 and F2, where F1 is equal to F2. So just for denotation, I am writing it like this, but the force, both forces are the same one. Okay, so for force F1, sorry, so force array. So for force F1, what is the R value here? It is 0. Okay. So, and for force F2, what is the R value here? It is, let's say I write this as A and this write this as A. So this is equal to A plus A, which is equal to 2A. So therefore, what is the moment at A? Moment at A is nothing equal to 2AF. Okay. It is clear. Let us try to calculate magnitude at B. Okay. Sorry, moment at B. Moment at B. So for moment at B, if you see clearly, this is in anti-clockwise sense only. Okay, now let us calculate the magnitude at B. So for calculating the magnitude at B, what we can say, let us first calculate for F1. So it's F1 into A. If you see clearly, it is in anti-clockwise sense only, plus F2 into A. If you see clearly, it is also in anti-clockwise sense only. So therefore, the magnitudes of same direction can be added directly. So it is nothing but 2A into F, which is an anti-clockwise direction because F1 is equal to F2 is equal to F. Now let us calculate at some point C. So if we calculate point C, F1 into 2A which will be again in anti-clockwise sense, plus F2 into 0. Why 0? Because there is no value of distance between the point C and the direction or application of point F2, force F2. So therefore, this is also equal to 2AF in anti-clockwise. So if you see clearly, to all the moments we calculated, all are having same values. Okay, so hence this is proof that even if you change the position, the values of the moment calculated will always be same for the couple. And what is its value? It's the value of the individual force magnitude multiplied by the distance between, perpendicular distance between. Okay, so I hope this question is clear to you. Now let us move to another concept, which is basically called as principle of movements. Okay, so just put a little bit concentration here. You will understand this, a very small concept, so that basically this is one of the applications. This can be understood as one of the application of use of your rotational motion or use of your moment concept, etc. Let us try to understand that and then we'll move forward. Okay. So first of all, let me make you understand what is basically a fulcrum. So basically, what's a fulcrum? Okay. So an ideal lever, basically an ideal lever is essentially a light rod pivoted at a point. Is a light rod pivoted at a point. Is a light rod pivoted at a point along its length. Fine. So this point, so basically, let me write. So this point we are talking about here is basically called as fulcrum. Is called the fulcrum. Okay. So basic meaning. So basically, this point R, this triangle is basically your fulcrum. Okay, so you may have seen this type of figure. So basically what is happening here, you can see that this is a simple example of a seesaw. There's a fulcrum being obtained and there are two forces being acted upon downward direction. You can assume that those to be gravitational forces acting in downward direction. Fine. So now let us try to find the equilibrium of this this complete rigid body. Okay. So here for translation equilibrium, what we can write? So let me go very slowly. So for translational equilibrium, we can write basically, let us assume, so there is no need to assume, we can write it R is nothing but equal to F1 plus F2. Right? For x direction, it will be 0 only, there is no use of writing that. And similarly, now let us try to calculate for rotational equilibrium. So for rotational equilibrium, let us calculate the magnitudes at let us suppose point R only. Okay, so we calculate from point R, we can say it is nothing but equal to F2 into D2, which is in clockwise sense, plus F1 into D1, which is in, if you see clearly, it's anti-clockwise. So we can basically write it as also minus F1 into D1, which is in clockwise, or in another form, in more mathematical sense, we can directly shift one of those forces on the right hand side. So therefore we can write F1 D1 is nothing but equal to F2 D2. Okay, so I hope it is clear till this position. Now let me define some more concepts here. So here let me just write those. Okay, so in the case of a lever, F1 is basically the weight which is to be pulled, or which is a weight to be lifted. Okay, and hence this is also called as your load. Okay, first concept. Second concept is that the distance which is being used for this, basically D1, is the distance at which it is kept from the fulcrum, and hence this is also called as your load R. Fine, I hope it is understood now. I'm just telling the definitions. Okay, similarly F2 is basically the effort applied to lift the load. Okay, so it is the effort applied to lift the load, right? And hence this is called as effort. And what is D2 basically? D2 is nothing but your effort arm. Okay, so that being said, Now, basically what we can write this equation is also equal to nothing but load into load arm is equal to effort into effort arm. Okay. So above equation basically expresses the principle of moments of a lever. So basically this above equation expresses the principle of moments of a lever. Principle of moments of a lever. Okay, so let me stop the discussion here only because the next concept will take time to make you understand. So I won't go into very fast pace here. I want to make you understand very slowly. Let me stop it here only. So the final conclusion of this concept till now is we understood what is the meaning of fulcrum. We understood something called as load, something called as load arm, something called as effort and effort arm, and basically derived this equation. And just for reference, right now we can understand that this is nothing but your this equation basically expresses the principle of moments of a lever. Okay, so that thing being said, let me stop this discussion here only. So the course progress for you, we started with the introduction, completed the center of mass, completed the motion of center of mass, completed linear momentum system of particles, completed vector product of two vectors, completed the angular velocity and its relation with linear velocity, completed torque and angular momentum, and currently we are on the equilibrium of moment rigid body. That is its subtopic. After this, we'll go to the most important concept which you need to understand. That is the moment of inertia. Okay. So I won't go into anything right now. I won't explain anything right now. When we'll understand that, we'll go very slowly and understand each of these concepts. Okay. I will try to make you explain the moment of inertia of all the bodies. We'll do differential equations. We'll use different concepts. Try to find out the moment of inertia of all the different shapes which are possible. The simple basic shapes. So that thing being said, let me stop the discussion here only. We'll first complete 8th subtopic and then we'll move on to the 9th subtopic, that is moment of inertia. Okay. So that thing being said, let me stop the discussion here only. So thank you so much. We'll meet in the next lecture.